Okay, let me start by recapitulating a few things that we have done so far. So we have learned about various kinds of quantities. So we have learned about scalars, which you of course know. Examples are example of scalars would be, let's say, temperature, density. This you already know. Then we have vectors. You know, examples of vectors are what? Velocity, acceleration, electric fields, etc. And then we have learned about this new animal called tensors. And mostly we have talked about second order tensors. We have not learned many examples of this. We will do that in the course of this course of ME321. But I'll give you some examples. So we are going to learn about stress, strain. These are going to be second order tensors. And then we have also um, also learned that tensors, the idea of tensors can be generalized to any order. So you have higher order tensors as well. Uh, and mostly the examples that we will encounter are of fourth order tensors, and elastic stiffness that we will learn about later is one example of fourth order tensor. We also sometimes deal with third order tensors, in though we will not do that in this course. And for example, strain gradient of strain, we will learn about what gradients are, and gradient of strain is an example of a third order tensor. So we have learned about all these quantities, all these different kinds of quantities, and basically, try and close this. Okay. Basically, the definition starts with the idea of a dyadic product, which we have defined here. Which we have defined here in the last class. So the dyadic, once we have defined the dyadic product of two vectors through this relation, we made the point that any tensor has the dyadic product of the base vectors, of the Cartesian base vectors E1, E2, E3 as its basis. So a second order tensor has EI dyadic EJ as its basis. A first order tensor, that's a vector, has just EI as its basis. A third order tensor would have EI, EJ, EK as its basis. Fourth order would have EI, EK, EJ, EK, EL as its basis, and so on and so forth. So you can define any order tensor with a suitable basis in the Cartesian coordinate system. And also what we have learned is that the components of a second order tensor, which we have written as Tij here, so Tij would depend on the components themselves, would depend on the coordinate system that you are using. In this case, we are using a fixed Cartesian coordinate system. So Tij are components in that fixed Cartesian coordinate system that we have chosen. The tensor T is, of course, doesn't care about what you have used to. It's a physical quantity that exists, and it doesn't care about the coordinates that you have used to describe it, but the components do care about the coordinate system that you have used. So the idea of the dyadic product, which is embodied in this definition, is actually the basis by which we can generalize the concept of vectors which have only one base vector, a dyadic of one base vector uh, as its basis, to any order tensor, provided we make up the base vectors in the make up the bases using a correct number of dyadic products. Okay, so this is where we started from, and then we looked at the ways of extracting components of a second order tensor from the tensor itself. So we made the point that to extract the ijth component of a tensor, you need to post multiply by j and pre multiply by I. Again, a is a second order tensor. This ej is a first order tensor or a vector. So when we write the product of them, we don't put a dot. Uh, However, A times Ej is a vector and Ei is also a vector. So we put a dot between them to signify that the final result is a scalar, which is the ijth component. So this is the way in which we extract the component of a tensor in the ijth component of a tensor. Okay, so this is another important thing that we learned. The other important thing that I thought I should mention in this recapitulation exercise is that a second order tensor uh, can be split into a symmetric and an anti-symmetric part, and this is how this is done. So the symmetric part is half A plus A transpose, where A is the second order tensor that we are trying to split, and the anti-symmetric part, so that the sum of these two is always the tensor itself. This is self-evident, but this is sometimes more sometimes very useful. We'll use this many times. There are other kinds of splittings possible. So A can be split up into a symmetric and an anti-symmetric as shown here. But there are other kinds of splittings possible, which we will deal with later when we learn about stresses and strains. Right. So what else? So any order tensor um, can be contracted with a tensor of any other order. So we have looked at these operations, and in these operations, when we do these operations, we have to see how many dots are there. Okay, so this is a third order, this was a third order tensor, this was a second order tensor. So we have two dots here, which means that the result of this operation would be a first order tensor or a vector, and that is how it is. So when you do this operation, you need to remember the order in which you will operate on the um, base vector. So the first one is a third order tensor, the second one is a second order tensor, and when we operate, we go at it like this: the last with the last, then the second last with the second last, and then the third last with the third last, and so on. And just if something is left, so here you did the last with the last, the second last with the second last, then EI was left. EI has nobody to pair to on the right hand side, so EI is left, and therefore the result is a first order tensor or a vector. So this is the multiplication, the contraction order that we are going to follow. If you don't follow this, you would get a different set of indices here. You need to be consistent with the order in which you operate, so that you always get the same set of same ordering of indices as I have got in this. Otherwise, you will get a different ordering. So this is how you operate on tensors. Finally, fourth order tensors have two identity uh, identity matrices. One that multiplies with the tensor to give you the transpose, multiplies with the second order tensor to give its transpose, another which multiplies with the second order tensor to give the tensor itself. So these two identity tensors are fourth order identity tensors, and in the space of second order tensors, you have only one identity tensor, one kind of identity tensor, whose whose components are delta ij in the Cartesian system. Uh, Whereas for fourth order tensors, you have two identity tensors, and we will use this fact uh, later in the course. Now, even after this, people ask what the hell is a tensor. So, well, the answer probably lies here in the transformation um, rule. So, tensor is a quantity that transforms according to the rules that we have defined here. So, for example, this is the transformation rule for a first order tensor or a vector. So, uh, as I said, the vector itself is doesn't care about the coordinate system that you have chosen to describe it. So, if you know the components of a vector in one coordinate system, you have this rule to get the components in a new rotated coordinate system. So, these components would be in a new rotated coordinate system given by this transformation rule. So any quantity that obeys this kind of transformation rule, whereby the components in one, if we know the components in one coordinate system, we can get the components in another coordinate system, would qualify as a tensor of some kind. Uh, this is extendable, as we have seen. So for second order tensors, this is the rule that we follow for transformation from old coordinate systems to new coordinate system, and from new coordinate system to old coordinate system, it's the reverse transformation. But look at this transformation. This is just an extension of the way we transform vectors. We had one Q for vectors, we have two Qs for second order tensor, we'll have three for third order tensors, and so on. So this is a completely generalizable transformation rule by which the components of the quantity in one coordinate system should be available in another coordinate system if you apply the transformation rule correctly. Which means that if the components of this physical quantity is known in one coordinate system, it is always known in another coordinate system, provided we know the transformation matrix, transformation tensor between the two coordinate systems. So any quantity that follows this rule would qualify as a tensor. To qualify as a tensor, second order tensor, you just don't need, it just doesn't suffice to have 9 numbers arranged as a matrix. Those 9 numbers must represent a physical quantity that transforms according to this rule. So this transformation rule is extremely important to prove that something is indeed a tensor. Something that transforms in this way only and only can be called a second order tensor. Okay, so this is the basic idea behind tensors, that it obeys transformation rule, which is like this for second order tensor and completely generalizable to tensors of any order. Now a special transformation is the eigenvalues and eigenvectors. So for symmetric tensors, we talked about eigenvalues and eigenvectors, and you know how to calculate eigenvalues and eigenvectors. But what we mentioned in the previous week was that the eigenvectors are invariant. So the eigenvectors and eigenvalues that you get for a particular second order tensor, let's say A, are invariants in the sense that no matter which coordinate system you use to represent A, no matter which coordinate system you represent A in, you will always get the same set of eigenvalues and eigenvectors. Not only that, there are some quantities called scalar invariants. For second order tensors, they are I1, I2, I3 defined in this manner. I3 is the determinant of A, I2 is the trace of A, and I1 is the trace of A, and I2 is trace A square minus trace of A square. So these invariants also don't care about which coordinate system you have expressed A in, which means that you can express A in any coordinate system. Its determinant will always be the same. Its trace will always be the same, and this quantity I2 will always be the same. Uh, that apart, we also learned that we can take the eigenvectors of A as a bona fide basis vector for a coordinate system. It will be a different coordinate system than the one that I have chosen to describe it in the x5, x1, x2, x3 space. So if I rotate now A using transformation rules into that coordinate system, which is formed by the basis vectors that are its eigenvectors, normalized eigenvectors, then A becomes a diagonal matrix. Okay, the components of A in the space spanned by its normalized eigenvectors are form a diagonal matrix, and the diagonal quantities are its eigenvalues lambda 1, lambda 2, lambda 3. So trace would also be lambda 1 plus lambda 2 plus lambda 3 in that coordinate system, and since trace is invariant, it would be lambda 1 plus lambda 2 plus lambda 3 in any coordinate system. Okay, and it will be this, I2 will be this in any coordinate system, I3 would be this in any coordinate system. So the special coordinate system is called the principal directions, and you can represent a second order tensor in terms of its eigenvalues in the space spanned by its normalized eigenvectors. The space span, remember A is a second order tensor, so it is spanned by the dyadic product of the basis vectors. In the space that is spanned by its normalized eigenvectors, the dyadics are n alpha, n1, 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 n2, n1, n3, n1, n2, n1, etc. Out of those, only n1, n1, n2, n2, n3, n3 have non-zero values, non-zero components, and those components are lambda 1, lambda 2, and lambda 3 respectively. All other like n1, n2 or n1, n3 have zero components, so they are not mentioned here. So this expression gives what is known as the spectral representation of a second order tensor, and this is also very important because, as we'll learn later, this is the idea that we have behind principal values and principal directions of stress and strain tensors that we have learned earlier. So this is all the recapitulation that I needed to do. I will stop the recapitulation now, and we will start with something new after this.